In this video, I'm going to go through an example of sketching a curve using the derivative tests. We're going to use the derivative test to sketch 3x to the fifth minus 5x to the fourth. Now we know generally what this shape is going to look like since it's a polynomial. I always like to start off thinking about what should the domain be. So we know for a polynomial, the domain is going to be all real numbers, so negative infinity to infinity. Then if possible, I try to find the x and the y intercepts. So first I found my x-intercept by setting the polynomial equal to 0 and factoring. So I have an intercept at 0, 0, and another intercept at 5/3 0. That means my y-intercept is at 0, 0 as well. Next is to use the first and second derivative test. Remember, the first derivative test is going to tell me if there are any extreme values, so a maximum or a minimum, or possibly multiple max or a min. And it will also tell me the intervals for which my function is increasing or decreasing. So taking the first derivative of this polynomial, then setting it equal to 0 is how we start the first derivative test. I get two critical values, one at 0 and one at 4/3. I'm going to build my sign diagram and test each region to determine whether my function is increasing or decreasing. For values that are less than 0, our function is increasing. If we're between 0 and 4/3, we're decreasing. And if we're greater than 4/3, we are increasing. Remember, when testing the values, we're plugging in our sample values into the first derivative to find the positive and negative. That means I'm increasing from negative infinity to 0 and 4/3 to infinity. I'm decreasing from 0 to 4/3, and I have two extreme values. So I have a maximum at 0, 0, and a minimum at 4/3, comma, negative 256 over 81. Negative 256 over 81 is roughly negative 3.16. Lastly, we're going to use the second derivative test to determine the intervals of concavity and if we have any inflection points. So I took my second derivative and then set that equal to 0, and I found two possible inflection points at 0 and 1. Built my sign diagram and tested the different regions, and I found that I'm concave down from negative infinity to 1, and then concave up from 1 to infinity. That means I only have one inflection point at 1, negative 2. So here's all the different pieces of information we have found. Well, we knew that the domain was negative infinity to infinity. We had two x-intercepts and our y-intercept. We knew that we're increasing from negative infinity to 0, then decreasing from 0 to 4/3, then increasing from 4/3 to infinity. That means I have two extreme values at 0, 0, and 4/3, comma, negative 256 over 81. Lastly, I know that I'm concave up from 1 to infinity and concave down from negative infinity to 1, which means there's an inflection point at 1, negative 2. Now that we have all of these pieces of information, we can graph them on the xy plane, which was the whole point of this. So I'm going to start by plotting my x-intercepts, my y-intercept, my extrema, and my inflection points.
Help.
You're going to help?
Yeah.
Okay. Why don't you just watch mommy for 1 minute and then I'll let you help, okay? Okay, so I'm going to start off by plotting our extreme values as well as any points of inflection and intercepts. So I have 0, 0. I have 5/3 0. I have 4/3 negative 256 over 81. So like I said, that's roughly negative 3.16. And I have 1, negative 2. So I know that I'm concave down from negative infinity all the way to 1. And that I am first increasing up to 0. From 0 to 4/3, I'm decreasing. So here I'm decreasing in concave down, then I'm decreasing in concave up. Remember, 4/3 is where I'm going to change direction into increasing. It was where x is equal to 1 is where I changed my concavity. I am now starting with 1, already concave up, and then starting at 4/3, I'm now going to be increasing again. So this is a rough sketch of what my function looks like, which is similar to what you would get with your graphing calculator, as you could see inserted here.